Okay. So let's see. So, like I said, I'm going to cover a lot of things in periods of time when significant things happen. And eventually, I'm going to get to the last 2 years, which are where the important things happened. Okay, actually, they started in 2015, but most of the exciting stuff happened in the last 2 years. Okay, so in November 1915, as everybody knows, Einstein finally got his field theory of gravity known as general relativity. It was a 4 set of lectures given at the Prussian Academy of Science in Berlin, and he came eventually with this equation, and that's supposed to be a 2, not an @ sign. So everybody eventually called it G mu nu, which is the gravitational tensor, and it's a combination of curvature, and on the other side you also have curvature, and the T is what is usually called the energy density stress pressure tensor. And the mathematics of these equations are long and involved, but John Wheeler said something close to this, not exactly this. The mass, energy, momentum, tensor, pressure, stress tells space-time how to curve, while space-time tells matter how to move. And that's sort of what's going on in equation 1. So these are classical physics, not quantum physics. And we're going to eventually talk about how we're going to get the connection between quantum field theory and gravitational field theory. So you don't have to understand the equations, as I said prior. I'm going to try to explain what the equations say, and we'll do a little bit of familiarity with high school algebra. I don't think anything more than about, if you know what x squared means, you're in good shape. You might think of Einstein's equations as E equals mc squared. He actually never wrote it that way. He wrote it as m equals E divided by c squared, because he realized that there was and that the inertial effect could be for energy, and all you had to do was divide by c squared, and you had the same inertia in the energy. So, but that's not what physicists call Einstein's equation. It's the one I showed previously. Okay, it's not a secret. You can find it everywhere. In fact, in 1905, he came up with his just amazing year. I can't remember what the name of it was, but it was his, they had the same thing for the year for Newton. And, he did 5 different articles in 1905, all of which— I think
they called it a miracle year.
Something like that, yeah. Anyway, all 5 of those should have gotten him a Nobel Prize. Unfortunately, only one of them did. And then, of course, his 1916 paper, which summarized the 4 lectures that he did in 1915. Those should have gotten another 6th Nobel Prize, but such is the life of a physicist. He thought about special relativity, which he was a great physicist, not a great mathematician. But he did understand that Newton's gravity did not work in special relativity. And he wanted to generalize the special relativity to include gravity. And he worked on it for 10 years, 1905 to 1915. It turned out to be a lot harder than he expected. In 1907, he had what he called the happiest thought of my life. And this was what we now call the equivalence principle. If you're in an elevator falling freely to the earth, you'll feel no gravity. So an accelerating frame of reference provides a solution, at least locally, to eliminate gravity. And initially, that was all that was needed, at least for constant acceleration. And he, in 1907, in an article for the Jahrbuch der Radioaktivität, he wrote a long article about special relativity. And the very last section of it, he used the constant acceleration in special relativity to show that gravity would create time dilation. And this is equivalent to what general relativity creates for time dilation. And this construction, the same one that he used, is now called the Rindler wedge.
Bob, quick question.
Yeah.
The elevator example, the feels no gravity, isn't that just what an astronaut feels in space?
Sorry, say it again.
Isn't that just what an astronaut feels in space when they're orbiting? I mean, they're continuously falling.
Yes, but for a different reason. There's a hell of a lot of gravity in orbit.
Which is what's keeping you
so you're falling back
right
to the earth as you're going forward.
Right.
So there's a combination of two there's a vector effect that is going on. And yes, the reason you don't feel it is because you're falling to the earth. The reason you don't fall to the earth is because you're falling forward at the same time. Yeah.
So, but you're
yes,
freely falling. You're not feeling gravity because you're continuously freely falling.
Yes,
That's correct.
That's correct.
Yeah. Got it. Okay. So he hadn't thought much about astronauts, but the elevator worked for him.
Well, yeah, there were no astronauts back then.
No, I mean facetious.
Okay. So he continued to try to make the principle of equivalence a symmetry of the universe, and he tried to make it a global symmetry. It wasn't until 1912 that Einstein realized that the principle was only local. And he also finally accepted what his mathematics teacher, Hermann Minkowski, talked about the fact that I think I have the exact quote in here about how there is a connection between space and time, and it is a four-dimensional time, not space-time, not a space and time separately, the way Newton thought of it, and which until about 1910 or so, Einstein also thought about them as being sort of separate, although the time was observer dependent, and but eventually he realized that Minkowski was correct, and he needed to understand the geometry of space-time in order to be able to understand how gravity worked. So he had, luckily, a mathematician friend, Marcel Grossman, who knew about Riemann's work on geometry, and he taught Einstein about Riemann geometry. Okay, now Bernard Riemann was a student of Gauss, and after receiving his PhD in Germany, before you could teach at a university or be available to be a full professor, you had to get what was called your habilitation. And Bernard talked to Gauss and said, "What should I write for my habilitation?" And Gauss said, "Give me a list." Whoops. Okay. Give me a list of possible topics. Riemann gave him a list, and Gauss chose the one that Riemann thought was the most boring. This was the foundations of geometry. Riemann gave a complete solution in a very brief paper, and this material was based on the use of the length of distance between points in space. Now, we always think about it as, a squared plus b squared equals c squared, or a squared plus b squared plus c squared equals d squared, whatever, in 3 dimensions. But what Riemann thought and developed was, we actually need a 3x3 matrix, that is a set of 9 numbers at every point in space, in order to compute those distances. And his initial paper was not very extensive because he thought it was boring. And many other mathematicians finished his work after he died in his 40s by tuberculosis. The names you might have heard of are Ricci and Christoffel, and many others made important developments. So using the matrix formulation, if you have this 9 set of numbers, gxx, gxy, gxy, gyx, gyy, etc., all 9 numbers at every point in space, then if you have little dx's and dy's and dz's, you can get the length by getting the inner products of those 2 vectors, and that gives you the equation, the second equation shown. And if you use subscripts, you can write it using summation signs, and Einstein got tired of writing summation signs, So he created what's called the Einstein summation convention. If you have two indices, one up, one down, then you sum over it. So the A's are up and down here, so that is equivalent to having this sum. And the B is down and up, and that's equivalent to this sum. So this is the shorter way to write this one here. This is the shorter way to write this one, which is the way, this is the way Riemann wrote it. Now, of course, Riemann was only thinking about space, not space-time.
Bob, before you go on, could you just tell us what S is and DS?
S is the length between 2 points. So the distance between those in X, Y, and Z coordinates are dx, dy, and dz. And the length between those 2 points in space is called S or ds. And this is a generalization of the Pythagorean. If you had everything being just diagonal, that is 0, 0, 0, 0, 0, then this would give you the Pythagorean theorem. That is, there'd only be 3 numbers, and in that one, it would all be ones. So you'd get ds squared equals dx squared plus dy squared plus dz squared. But he said, well, in an arbitrary space, which is not flat the way Euclid's space was assumed, then you need 9 numbers at every point in space. And
If I could just add something to that.
Sure.
Sorry for the interruption, but you can think of X, Y, and Z as coordinates that you lay out. They don't necessarily have to be orthogonal. And what the G's do is convert these coordinates, which can be quite arbitrary. You can think of them as city blocks, or if you're going to lay out a street grid, and label it 1, 2, 3, 4 for each block that you go. But to convert those to distance, you need these metric quantities, the G's. So it's a way of converting coordinate intervals to actual distance intervals. And of course, the conversion depends on whether you're in a flat space or a curved space.
Yep.
And
So-
that,
Could we could we take a example of a curved space like the surface of the Earth? And the distance between New York and say Sydney, Australia, would this represent that distance if you followed the surface of the Earth?
you'd have to integrate along to get the distance, to get an actual distance, you'd have to pick a path. And
Right, this
yes.
would give you, remember, these are all differentials. So the key insight that Newton had in mathematics, and that is the heart of mathematics for the last 300 years, is that you have to get everything really, really small in order to get everything to work out. So you get really, really close to a point and you get these little tiny distances, dx, dy, dz. And then after you've gotten that distance, you go, just a tiny distance away, and you do it again, and you do it again, and you do it again, and then you add it all together. And that is the insight that Newton had in creating differential geometry, in differentiation and integration. So this is the insight that mathematicians use forever and have used forever. And so this is, the idea is you do everything really, really close, and then you add it all together. So yes, you could, but you have to do it by knowing every of those 9 numbers at any point on the surface of actually on the surface of a sphere, it's only 2-dimensional. So it would be 4 numbers at every point in space.
So let me follow up just a little bit more. When I was in grade school, the teacher told me if I wanted to know the distance between New York and Sydney, I would put a string on the globe with one end of the string in New York and the other end of this string in Sydney, and that would be the distance
Well,
on the
that's,
globe.
yeah,
Does
but the way in which you have to get that, you're basically taking the curved surface, the line, which is a curved surface, and you make it into little tiny little pieces and add them all together to get the length.
Yeah, and if I did that, would that be I would get S if I did what you said. Instead of DS, I would get a thing called S. And would
Yeah.
that be the length?
Yeah, you got it. Now,
would
the
that be
thing
the
is,
length?
though, you have a coordinate system on the Earth as it is, latitude and longitude, all right? But if you go 10 degrees in longitude to 20 degrees in longitude at the same latitude, that doesn't tell you the distance. You have to convert latitude and longitudes to distances. And the formula, the DS, those G's do that. Now, to answer your problem about stretching a string, you pick a path from London or wherever you're starting from to Sydney and integrate DS along that path. That gets you the distance, but it's not necessarily the distance that you get if you took a string and did that. You'd have to then, once you got that distance, you'd have to ask, what is the minimum distance? What path would give me the minimum distance? Okay, so you pick a lot of different paths and you find the one that gives you the minimum distance, and that's the one that you'd get if you were to stretch a string.
Yeah. Okay. So yeah, you stretch the string.
Yeah,
And so
mathematically, it's called a variational problem. It's take one path among many that actually minimizes that distance.
is that the same as a great circle on the Earth?
Yeah.
Yep, that's
Yeah.
exactly the same.
One more quick question.
Sure.
X, Y, Z are then just not obviously Cartesian. They're any 3 lines.
That's
any 3
right.
directions.
Right,
Can-
right.
And
Yeah.
can they obviously vary, I might say, from point to point in space.
Yep.
That's right.
Yeah.
So the
right.
G's vary from point to point.
Yeah, and that, it's interesting. I've seen this kind of before, but this one slide put together this way, and the explanation is the first time it's actually really made sense to me. So thank you.
You're welcome. I'm glad we could get something out of this. We'll keep trying. All right. Back to Herman Minkowski in 1908. He had he was a great mathematician, and there was the 80th Assembly of German natural scientists and physicists, and he was asked to give the opening statement. And his opening sentence is the following one. Gentlemen, the concepts about time and space, which I would like to develop before you today, have grown on experimental physical grounds. Herein lies their strength. Their tendency is radical. Henceforth, space for itself and time for itself shall completely reduce to a mere shadow, and only some sort of union of the two shall preserve independence. So Newton had assumed that space was completely separate, independent of space, of time. And he also assumed that every observer measured the identical time. Every point in the universe, time went on simultaneously. What Einstein had shown in 1905 was that was completely wrong. Time was a function of the observer. Every time is measured by the clocks on a particular observer, and they will not click at the same rates at every watch simultaneously, the way Newton had assumed. And in point of fact, you can rotate time into space and space into time. So all of these things were implicit in Einstein's 1905, and it was Minkowski who understood that this made them a unified space-time. And this particular sentence was the first time that anybody in physics realized that there was such a thing as space-time. Now, Einstein, as I said, he was a great physicist, but not a great mathematician. And he, in the same year, wrote, "Since the mathematicians have invaded the theory of relativity, I do not understand it myself anymore." So he was very smart, but he learned only as much mathematics as he needed to do his physics. Hermann Minkowski was his teacher at university and said to him, "You are a smart boy, but a lazy dog." And of course, being smart, Einstein eventually recognized what Minkowski was saying, but it wasn't until about 1912 and his friend Marcel Grossman, who taught him Riemann geometry, that general relativity was finally on the right track.
Bob, another quick question.
Sure.
Up until this time, was it every measurement of time based on gravity in basically the same reference frame? In other words, in the Earth?
Well, yeah, but you know, it depends upon how accurately you could measure things at the time.
That's what I'm saying. Yeah, that's what I'm saying. But everybody measured time based on, you know, mechanical clocks of some sort or another, or pendulum, something like that. So gravity was being used as the fundamental physical driver of measuring time.
Well, or springs or whatever.
Well, that's mechanical. I mean,
it's mechanical, but it's not gravity.
But the springs springs still drove things that were oscillating, or I'm just trying to figure out how you know. Okay.
Yeah, but you just have, you know, gears being set up to move a certain amount every time they clicked. So yes, you're right. It was mechanical, but it wasn't always gravity.
It wasn't gravity. It wasn't. There
is a force that needed to be used to make things.
Either a mechanical force, like you say, a spring force, or gravity was the driver. Okay. Good.
Right.
Thank you.
Right.
Yeah.
And actually the time was based on rotations of the Earth. That was the basis of the rotation of the Earth around the Earth being 24 hours. And then you develop it into hours, into minutes and seconds and whatever, amount of
but I meant just knowing I'm right now, and then at some whatever I call it, a second, a minute, or a quark, it was still done as a result of the movement of some physical entity, be it a pendulum or a spring or something like that. There was something you could see. It was
Right, but
Yeah.
Newton thought that time was universal and everybody measured time exactly the same way.
right, and it was this
And-
flowing thing.
And yeah, and Einstein in 1905 showed that that wasn't true.
Got it.
Every watch on a different observer had a different time. So that was really rather changed. So anyway, eventually, based on Grossman's work, Einstein realized that the Riemann curvature, which has 4 indexes, and each one is 4-dimensional, so it has 256 components. But the energy stress pressure tensor has only 9 components. So he couldn't make gravity out of Riemann curvature. And if you go to the Ricci curvature tensor, which is a summation over various subscripts of the Riemann curvature, then you would get a 16 4x4 curvature tensor. So several times between 1912 and 1915, he tried to use R sub mu nu, which is the 16 component is equal to the 16 components of the stress energy tensor. But it led to inconsistencies. Now, there is another curvature, the scalar curvature, which you can sum over various combinations of the Ricci tensor, and that gives you a constant. And he wanted to use it, but he didn't. Well, let's see, what did I say here? Einstein had his oh yeah, in 1915 he finally had his general theory of relativity. The curvature is a generalization of the Cartesian acceleration and the equivalence principle raised to a postulate. And the mass is those 4x4 array numbers of components, the TT component, where T is time, and that has energy density. And then there's a TX and a TY and a TZ, TXX, TXY, all of that whole 16 set of numbers. Turns out that because of various symmetries, there's only 6 independent numbers, but we won't talk about that itself. Okay, but everything in the pressure, energy density, all of the various stress, strain, flow of heat, anything that has energy acting around, that is what's in the stress energy tensor. And that is what is the equivalent of mass in Newton's gravity. So the form in which Einstein used his equation on energy, m equals E over c squared, is essentially the T mu nu is all of the various components of energy divided by c squared. That's where the c squared on the bottom comes from. So it turned out that you needed to add that constant R next to the 16 numbers, and add that to the Ricci curvature, and that is what his equations finally developed in his 4 lectures in November 1915. Now, Hilbert actually a couple of times in 1912 and then again in 1915, Einstein went to Göttingen and gave lectures about his general relativity. He lived at Hilbert's. And they talked about it continuously while he was there. And eventually, after the 1915 set of seminars that he presented, Hilbert realized that he could use the action principle to generate general relativity or gravity. And we'll never know, because both Hilbert's published article was revised several times before it was finally published, and Einstein's 1916 version of his 1915 lectures was also revised several times. So it may be that Hilbert actually got these equations faster, just before Einstein did. But Hilbert always said that Einstein created general relativity. He never claimed he did anything in that other than using a different way to get to the equations. What about Schwarzschild? Well, when Einstein was solving these equations or developing them, whatever you want to say, when he was solving those equations, he always used perturbation theory. He never had an analytic solution, and he thought it would take 100 years before anyone could find an analytic solution. Schwarzschild was an astronomer colleague of Einstein and also a soldier on the Western Front in World War I. During his time off, he went to Berlin and heard Einstein talk about his nascent theory of gravity. And during the day, he computed artillery trajectories, and at night, he solved Einstein's field equations.
Oh, Bob, just one correction. I think he was on the Eastern Front.
Oh, okay. I'll change that.
Doesn't change the physics very much.
No, it doesn't. Yes. Oh, you're right. He was on the Eastern Front because he was on the Russian side. Okay. Yes, I apologize. Okay. So in his 1915 lectures, he showed Newton's theory was equivalent purely in terms of space-time curvature. And he used a completely flat space, no spatial curvature whatsoever. To reproduce Newton's theory, he had this metric, 1 minus 2 times phi sub r divided by c squared, and ones going down the diagonal. So the ones going down the diagonal are just the ordinary Euclidean part of the space distance. So the first one is the time portion, and phi is Newton's gravitational potential, and that reproduces all of Newton's gravity. So in the same year, in a different paper, Einstein used an addition to the metric. He modified the phi to Newton's plus gx squared divided by r to the 3/2. This was an approximation, and he used in his 1915 paper he used this metric to that the same one except phi hat instead of phi. He used this approximation to provide the doubling of light deflection and the increase of 43 seconds per century in the perihelion of Mercury. So he was simply doing a perturbation, and this was the additional perturbation that he did, but everything just assumed that space was completely flat, no curvature in space. Anytime you see the trampoline with gravity pulling it down with a bowling ball or something like that, first of all, you're using gravity to show gravity, which is really stupid. And second of all, that's not what Einstein used in his papers. So you can use a completely flat space in order to get all the results of the solar system. The solar system is essentially flat. Okay, so in less than a few months after his 1915 lectures, Schwarzschild showed the solution. This was a complete universe without any mass. And if you define R sub S equal to GM over C squared, and it's a constant, and let R be the square root of X squared plus Y squared plus Z squared, then this set of 16 numbers at every point in space and time is the metric that Schwarzschild showed was the solution to Einstein's equations. This happens to be the Schwarzschild metric in Cartesian coordinates, that is T, X, Y, and Z. And the point of this is simply to reinforce that coordinate systems are creations of human beings and have no particular meaning. So the way in which Schwarzschild actually showed it was in spherical coordinates, which makes this considerably simpler. That is, you get everything diagonal, and the potential phi bar for the Schwarzschild solution is given by Newton's G rho divided by R minus L squared over 2R squared, where L squared is the angular momentum, and GL squared rho of R over R cubed is the third component. So the first and third terms were essentially close to the approximations that Einstein used in his perturbation theory. The two provide, I think, the same accuracy of four digits or something like that for the curving of a light beam around the sun, or the perihelion of Mercury. So they're slightly different, obviously, but very close. So, and in his 1916 paper, he had, of course, read this material by Schwarzschild and used it in his one of his later revisions of his 1915 papers, or lectures, I should say. Okay, after 1915, I already told you about Schwarzschild, David Hilbert and his work. And so now we want to get to the late 1960s, early 1970s. Jacob Bekenstein, like I said, we're going to jump around time a lot. We're moving to 2015 and later is where we're really getting to, but in the late 1960s and early 70s, Jacob Bekenstein, who's known as the father of black hole thermodynamics, had a celebrated insight. It came out of a famous conversation between Bekenstein and his PhD advisor, John Wheeler. Wheeler said, well, a hot cup of tea has entropy as its earliest macroscopic description admits many possible microstates. And we coarse grain it and we call it a cup of tea. So a black hole, on the other hand, at that point in time, has no entropy whatsoever. As far as they knew, there was absolutely no entropy. Because there's only three things that measure the qualities of a black hole, and that's their mass equivalence, the charge, and the angular momentum. So this Bekenstein had actually dubbed as the no-hair theorem, although most people usually think it was Wheeler. Wheeler was puzzled what happened. He said, if I throw that cup of tea into a black hole, initially the entropy of the system is given by the entropy of the cup of tea. But after the tea's fallen into the black hole, the total entropy is zero because only the black hole is left. The second law of thermodynamics says that entropy of a closed system can only increase. So has the second law been violated? Eventually, Bekenstein had an answer, and that was that the black hole must have an entropy. And as opposed to every other type of entropy, which is proportional to volume, he said, well, it's got to be proportional to its area, because a black hole only increases after absorbing a cup of tea, because it would expand the size of the black hole, and the area goes up directly. So Bekenstein based his insight not only on the teacup thought experiment, but then the recently proven theorems by Stephen Hawking and Roger Penrose that the area of a black hole can only increase. And Bekenstein realized that the non-decreasing of the black hole's area was reminiscent of the second law of thermodynamics. So the insight that he came to was not the one that most people would usually have thought about, because although the idea that a black hole must have entropy is something people worried about, why would it be proportional to the area? He reached those conclusions by applications of the second law, and as I said, to the fact that the area increases. So he dismissed higher powers than the area by considering changing the black hole area by a minimal amount, and he was able to come very remarkably close to the constant of proportionality, that it must be close to 1/2 log 2 in natural units. The exact value was 1/4, and it was determined 2 years later by Hawking, who wanted to prove that Bekenstein's ideas about black hole entropy were completely wrong. So Hawking went on a 2-year quest to prove Bekenstein wrong, and instead wound up showing that he was correct, got the exact answer instead of the proportionality that Bekenstein had used, and also had shown that because anything that has entropy will radiate, black holes also radiate. Therefore, they have a temperature, and all of this just, behaved exactly as Bekenstein had predicted. So this fixed the black hole entropy as the area in Planck units of area divided by 4. So that was the initial understanding. Now, Hawking assumed that he did a calculation. I'll go through it first. He, however, did feel that the information that fell into a black hole was forever lost. So the black hole information paradox was born, and it persisted until, well, you can think about it 2 different ways. 2009, I think, or something, 2007, 2009, something like that, was one insight, but it didn't mean much physically. And the last 2 years are where we're eventually going to get to about what the solution to the black hole information paradox has finally come somewhat close to finding. Okay, so how did Hawking do his calculations? He needed to use quantum field theory, which mathematicians have been trying to understand and make rigorous for about 100 years, all without success. So as far as mathematicians are concerned, quantum field theory is not can't be made rigorous. And general relativity is a classical field theory. It has a 4x4 array of numbers at every point in space and time, in space-time. As opposed, quantum field theory has an infinite by infinite square of numbers, also at every point in space and time, but in a different space, a Hilbert space, which is an infinite dimensional space. So how do you make those two work together? I mean, you got 4x4 and infinite by infinite, and one's in space and time, and the other one's in a Hilbert space, a completely independent space. Don't seem to know how to make that work. Well, averaging is the answer. If you average across the Hilbert space, you get a classical field, sort of. This is called the semi-classical quantum field theory. And it works well in Minkowski space-time, and not quite so much for general relativity spacetimes. You can make it in a curvature space, and that's actually what Hawking did, but you get these weird effects such as the loss of information. So there's lots of different ways you can think about this. One that I usually use is the Unruh effect. So suppose you're a Minkowski observer near a gravitational field. Okay. Since you yourself is not accelerated, you are accelerated. You're near a gravitational field, so you've got to be accelerated. So suppose you are an accelerated observer, then you see particles. If you're not accelerated, then you'll see nothing. That's one of the strange things about quantum field theory. The observer, it is just like special relativity and general relativity, it's observer dependent. So some observers see particles and others don't. So what goes on in the vicinity of the event horizon? Now, vicinity is a really loose use of word. For a black hole, say the size of M87, the Schwarzschild radius is larger than the solar system. So you can see in the image here from XKCD that the orbit of Pluto around the sun is slightly less than the Schwarzschild radius. So we're now the
Bob, do you have a logical place for a break?
Oh,
If we're going to take a
yeah,
break.
let me just finish this a little bit and then we'll break into that. Okay. The logarithmic mean of the vicinity near the event horizon is more than 20 times the Schwarzschild radius. That is much further than where Voyager 1 is right now. So when we say we're in the vicinity of the event horizon, we're not talking about something that is anywhere near Pluto. We're talking about something considerably further than Voyager 1. Okay, so how did this, well, I guess I'll leave this till we get back from our break. And just before we start our break, I want to let people know I have a dog walker for Prado coming somewhere between 11 and 11:30. So I will, when she comes and rings the bell, I will have to stop the lecture at that point and then let Prado, well, get the cat in the bedroom and then let the dog out and then come back. So I apologize in advance for all of that nonsense, but such is life. Okay,
Not a problem.
We'll come back to how the Hawking radiation is created, quote unquote, around the vicinity. Sometime the mean is more than 20 times the Schwarzschild radius, so it's really not very close. But we're going to call it the vicinity of the event horizon. Okay, well, let's take our break. And I'll be, let's see, it's now 11:06, so we'll be back at 11:11. Pause, record. Okay. So we're going to talk about vacuum polarization. Steve, this is where you might be able to add in. Polarization is something like an internal distortion or adjustment that a medium undergoes in a field to lower its energy. The result is the medium developing its own field. The induced field is directed opposite to the original field, and usually this is what happened, and there are some rare cases where a medium enhances the field, but it's not called polarization when it does. In the vacuum, there's always the possibility of virtual photons, virtual electron-positron pairs, whatever you want to call. And of course, many other things. Any excitation of any of the 18 or 20 fields, whatever there are in quantum field theory, any of those excitations can be created in either the antiparticle and the particle creation part. In terms of the temperatures we're talking about for Hawking radiation, a great majority of it is probably photons or gravitons, but let's just leave that go until we get to Don Page. So a pair is created, lives for some short amount of time, and annihilates. Now, this is all a matter of taste. You can believe that it actually happens, or you can just think it's an artifact of the perturbation expansion that's used for the calculation. In any case, let's just pretend that they really happen. Yeah. Okay.
Yeah, Bob, I guess you can think of vacuum polarization, which is what you're talking about, is like as if the vacuum was a dielectric.
Exactly. Yes,
Okay.
exactly. Dielectric is what causes the effect that I was talking about initially. Anyway, so we're going to treat them as real. And that means that each of them is affected by the gravitational field. And particles will travel on a circular arc trajectory, and each particle is a moving charge, so it'll create a magnetic field. There's all these effects that are occurred from the creation and annihilation of quantum field effects in the vacuum. And we're going to consider the net effect of them. And guess what? It's not zero. The bottom line is that the vacuum is affected by the strong gravitational field and produces a counter field, just like a diamagnetic medium. So Hawking radiation is not from coming inside the black hole, not even anywhere near its event horizon. As I said, the mean distance from the event horizon is 20 times the Schwarzschild radius. So it's, you know, we're talking about huge distances relative to the black hole. And at those distances, the gravitational field is considerably less than right at the event horizon. So vacuum polarization produces an equal number of positive and negative energy virtual particles, which in the absence of gravity promptly recombine into nothing, leaving us with, well, the vacuum. So in the presence of gravity, it is possible that a very few of the negative energy particles will fall into the gravitational field, that is, into the black hole. And when they do, they gain energy from that field. And they become real. What does it mean to be real? Well, in quantum field theory, being real means that the particle can go to infinity. That is, it's not going to recombine immediately. It can go off to infinity. So, excuse me, Kat, come on, I can't read with you in there. Yeah, thank you. Okay. As I said, the pairs aren't anywhere near the event horizon, but once a particle becomes real, only positive energy particles can escape to infinity. These are the rules of quantum field theory. So the negative energy real particle has only one place to go, namely the point of future time in the black hole. The point of future time is where they're removed from the universe and changed into curvature. So this is very roughly how Hawking radiation is purportedly created. You make a couple of real particles instead of virtual ones, and one of them, the positive one, by the rules of quantum field theory, can only escape to infinity. So the negative energy part goes into the black hole and hence reduces the mass of the black hole. So what do we know and what do we don't know? Or at least, well, we'll get there. So black holes exist. This is, you know, as the head of the National Science Foundation and astrophysicists said, they're the most mysterious objects in the universe. And the Sir Roger Penrose and Professors Andrea Ghez and Reinhard Genzel all got the Nobel Prize for their work on black holes. Sir Roger did it back in 1975 or so, roughly then. He showed that, you know, black holes were inevitable when stars collapsed, large stars collapsed. There was nothing you could do to avoid it. Everybody at the time thought, well, maybe it's chaos, it'll get out, and things get scattered, and you'll never form a black hole. But Sir Roger showed that was completely wrong. I believe Andrea Ghez and Reinhard Genzel were part of a team that created the description of the massive black hole at the center, at the quote center, unquote, of our galaxy. And they got the work for that.
Are they
Okay.
both, where are they both from? Because they both have the same robes on.
Yes.
I think
Steve might know.
one of them's from Germany. I think the other one is in Berkeley.
Well,
Yeah.
but they both have the same PhD robes on.
Well,
I
that
don't know what
doesn't,
those represent. Maybe those are just Nobel robes.
Or are they Nobel? I was curious. I mean, you know, for the other members here, they aren't,
I don't know.
they, you know, for the academic garb is something that's very archaic.
Yes, yes, absolutely. I listened to a Civil War podcast, and the historian every time tries to remember people, hey, I have a degree from Harvard, trying to make that mean something for the last 50 years or whatever it is he's been doing it. Anyway, yeah, people get all this stuff about that. All right, so black holes are a stage to provide gravitational phenomenon that we don't understand. That is very strong gravitational field of stuff. Deep inside black holes, or in the pre-inflationary universe, assuming you believe that inflation occurred, most physicists believe that general relativity breaks down because there is a point in future time called the singularity, which goes to infinity, and nobody believes that anything with infinity actually exists. So because of that, most physicists believe it's not a complete theory. When space-time is curved on quantum scales, something in the neighborhood of 10 to the minus 33 centimeters, the universe probably is not described by general relativity or semi-classical quantum field theory, but a real quantum theory of gravity is needed. The rub, except for quantum loop gravity, which most people don't really work with very much, we really don't have a quantum field theory. And so that's the problem. Black holes do exist, thanks LIGO, but our description of the universe is incomplete without a theory that accurately describes what happens at the point in future time in a black hole. So to repeat what Hawking found, if you have a weakly interacting general relativity and quantum field theory, that is a semi-classical quantum field theory, there's a limit that describes around the planet Earth very well, and that limit also describes the solar system, and finally there's a limit that we expect to be described near the event horizon of a sufficiently large black hole. So we have to think about it sufficiently large because black holes can be any size, including, you know, this size of a proton or less. And at that size, the curvature will be distinctly different than or it's believed to be different. Okay, so let's take a look at those competing predictions. Oh, I'm sorry. Yes, also the limit is used by Hawking in computing the entropy of a black hole. And the coarsest way of explaining the black hole information paradox is there's a conflict in two predictions of two theories in a regime where we don't expect them to have a conflict. Okay, so here's sort of the elevator pitch that you hear about the information paradox. Suppose you have two particles, Alice and Bob, and they're completely entangled. Alice ends up in the black hole. We have a picture of Alice going down the black hole, and Bob does not, but they're entangled. So I'll discuss about how black holes evaporate, but if the black hole evaporates, that means that the black hole will eventually disappear from the universe, from the system completely. And we conclude that even though we had entanglement, once the black hole no longer exists, all of the information about Alice has been lost. So that's usually the elevator pitch for the information paradox. A more mathematically precise way of saying that is that a pure quantum state, complete entanglement, appears to be evolving into a mixed state, no entanglement, once the black hole is evaporated, which is a violation of the unitarity of quantum mechanics. That is the U1 symmetry of quantum field theory. So that symmetry is a basis of quantum field theory, and that should never happen. So we've often seen non-unitarity, but that only happens in open systems. Open systems are systems which interact with the environment. And we've talked about decoherence, and that's what decoherence is all about. We're describing at a black hole of the Schwarzschild metric, which means the universe has no mass in it. So we're talking about only various kinds of massless particles falling in. And this is not an open system, it's a closed system. And the information loss would be a catastrophic. It would just destroy determinism in physics. So if we lose unitarity after the black hole evaporates, it's impossible to post-dict the past. So we cannot uniquely evolve the post-evaporation data that we could measure to determine what happened before the black hole evaporated. And that would be a loss of information. We end up with less information after the black hole is evaporated than before. And that means that physics is not post-dictive. That is, time reverse physics is not predictive. And that's a complete catastrophe, at least as far as I'm concerned. A complete catastrophic loss of determinism. So black holes exist, and there must be a definitive answer about the information loss. Understanding black holes hopefully will teach us about quantum gravity, but as long as we don't have a mathematical description of strong quantum effects, well, prior to 2019, the general perspective was that non-perturbative quantum gravity, full quantum gravity, was necessary to see evidence of unitarity in black hole evaporation. Basically, if you want to see unitarity conserve information, you have to be able to compute non-perturbative, strongly coupled effects. You have no hope of seeing unitarity unless you're in that particular unless we have a complete gravity, quantum gravity. Otherwise, it appears that you're losing information. In 2019, the gravity physics community realized there are ways, maybe, to seek information conservation, or at least some evidence of information conservation in semi-classical analysis. And that is what we're aiming for. This is the huge amount of activity that's been going on essentially since about 2005 or something like that. Anyway, we're going to talk about these insights for the rest of the lecture. So, life cycle of a black hole. So, on the right here, we have a picture of Stephen Hawking speaking to a student in his wheelchair. That picture was made by an artificial intelligence computer program called DALL-E. And I gave that sentence, Stephen Hawking speaking to a student in his wheelchair, and got 4 pictures out of DALL-E for that. And I thought the 4th one, which had both the student and Hawking in wheelchairs, was the most interesting one because I hadn't thought about that. So that's the one that I'm using here. Anyway, that's not a real picture. That's made by an artificial intelligence. So back to the life cycle of a black hole. First, you have to find a collection of gas and dust and let gravity do its thing. Let's consider a huge mass of dust, say 100 masses of the sun. Fusion eventually starts, and this pressure holds the star in the form of a sphere. So I'm going to use the vertical axis as time. And since we can only do 3 dimensions, I'm going to compress the z direction of the star so that well, that's interesting. That has not happened before. All right. Eventually, this was a movie that was going to show the thing going lower and lower, and eventually it was just a disk. So if you don't mind, I'm going to stop the recording and go deal with my. All right, as I said, we're going to be talking about little disks as being spheres just as we go forward. So, oh, come on, there. So as the star burns until its fusion fuel is exhausted, then gravity causes the star to infall. And because the star is large, I've said it's more than 100 times the mass of the sun. What Sir Roger showed was that you can't avoid the creation of a singularity and an event horizon, that is a black hole. So assuming a Schwarzschild black hole, I'll assume only massless bosons extending the size of the black hole. Basically, the CMB photons and random gravity waves are the only things that could increase the size of the Schwarzschild black hole. And the event horizon expands until the CMB, because of expansion, drops its wavelength longer than the Hawking radiation, and at this point, the Hawking radiation dominates and the event horizon decreases. So once it starts, it keeps getting stuff coming in, gets larger and larger and larger until eventually its radiation dominates and it then starts shrinking.
Bob, when you said on item 8, the event horizon expands, you didn't mean the universe, did you there?
Well, the event horizon expands because the stuff that'll be coming in is basically CMB photons. And so the event horizon will keep expanding until
Okay, got
the
you.
universe expands enough that the CMB drops its wavelength longer than the Hawking radiation. So there's two expansions going
Okay,
on.
so you're feeding the black hole with CMB radiation.
And random gravity waves.
Right, okay.
Yeah, yeah. And at this point, the Hawking radiation will then dominate and the event horizon will begin to decrease. So eventually the black hole will evaporate completely.
Right.
All right, come on. All right. So this is a picture from Sir Roger's 1975-ish paper that he got the Nobel Prize for. You have matter coming down. Once the fusion stops, matter starts collapsing. Eventually a trapped surface, the event horizon, and this is a disk here, it's really a sphere, is created, and the center line here is time, and that's the point of future time. I'm sorry, that's not really, the time goes this way from the outside to the inside, and the center is the location of the singularity. So a singularity is a point in future time. And while you're far away from the event horizon, you know, causality occurs in the usual ways, but eventually, once you get right on the event horizon, the light cones tilt enough that they can never get out. And in point of fact, they also shrink in size inside the black hole as well. So that's basically the story of how a black hole forms. And as I said, it gets larger as time goes on because other things fall into it. And at some point, so all of these disks here are spheres. And so you have the event horizon getting larger and larger until the universe expands enough that the CMB radiation is no longer able to feed it, at which point Hawking radiation dominates and eventually it evaporates at some point in time in the future. So that's the story I just told you about, in hopefully a way to see it in a visual.
Did anybody feel an earthquake here in the last couple minutes?
No.
My
No.
wife just came in and said, did I feel it? And I said, no, but then she just came in and there was a 5.1 in San Jose.
Wow.
Oh.
Yeah, I felt it.
Okay, I'm just gonna say, because I'm sitting in a little rocker, but I didn't feel it. I just was curious if I was going
Yeah.
numb or,
I haven't found
No.
it either, so.
okay.
Okay, so Stephen Hawking computed the entropy of a black hole and its radiation. Hawking stated incorrectly that the radiation was a black body. Kip Thorne and Stephen Hawking had a student, Don Page, at Caltech. Now, in 1976, 2 years after Hawking's calculation, Don computed the spectrum of Hawking radiation. It turned out not to be a black body, and he even got the spectra of emitted particles. Now, at the time, the standard model of particle physics assumed incorrectly that neutrinos were massless. And the spectra had approximately 60% massless particles with 30% neutrinos, and 35% were massless radiation, photons and gravitons. And the remainder were other kinds of quantum field excitations, electrons, quarks, whatever. So he got his PhD, he continued working. He's a great Canadian physicist, and as is Unruh. And in 1993, now we're up to 1993, Don computed at different information, that is entanglement entropy, instead of the entropy that Hawking had assumed. So he assumed that the particles entering the black hole were entangled, and all of their interactions with a black hole could be described by an S matrix. That is the way in which quantum field theory describes an interaction between anything. So Don computed what is now called the Page curve. And that should be an uppercase P because it's about Don Page, not some other page of paper or something like that. So this is the Don Page computed the entanglement entropy, and it's the blue dots. So it starts just like Hawking, it starts at 0, but it eventually goes to a maximum and then turns around and continues to go back until it goes back to 0 at some future time, the point at which the black hole has evaporated. The orange dots are Hawking information based on the assumption of black body radiation, and his just keeps going up until at the time it's evaporated, that's the maximum entropy. And basically he's assuming that everything that has been emitted is in equilibrium. So it's a thermal property. Whereas Don Page assumed that it's a quantum system and you start in a pure state, stay in a pure state, and then wind up at a pure state. So this is, the blue dots are quantum entropy, and the orange dots are more or less, although computed from quantum semi-classical quantum theory, they're essentially just traditional statistical physics entropy. So a rough intuition.
Bob, is there some way of, oh, you're about to explain that. I was wondering if there was some way of visualizing what was going on physically, because it seemed to me you are generating randomness up to a certain point, and then that randomness is beginning to become more and more organized, and the entropy goes down. I don't have a mental picture of exactly what's going on.
Well, the entropy is getting larger because the system is increasing. The size of the system is increasing. Initially, you start out in a pure state, and you have all of the quantum particles that interact via a S matrix are entangled with the black hole, and the size of the black hole gets larger. So the entropy calculation that Hawking did about the size of the black hole getting larger is still assumed on the quantum calculation to be identical. So as the size of the black hole gets larger, then the system gets large. You're talking about more and more stuff in the quantum state. Even though it's a pure state, it's got some quantum entropy, the size of the black hole divided by the Planck area. And then eventually, when all of the stuff everything that's moving gets interacting with the black hole is so you've got a larger and larger system that's in a pure state. And the increase in entropy is due to the larger system. Eventually, you run out of stuff coming in, and the stuff starts coming out. The assumption is whatever comes out is in a pure state. So the entropy is decreasing because the size of the system is getting smaller. Did that make sense?
Yes, it does. I just have to think about what it means, what the entropy of a pure state looks like. I don't have a good picture of that, but I'll think about that.
Okay. Anyway, so as I said, the black hole, we can think of it as a pure state, and the entire quantum system first getting larger as more stuff gets added onto the black hole. You can purify it by expanding the size of the system. And eventually, once the system goes to its maximum size and starts decreasing, then when the radiation is emitted, you reduce the size of the system, and the entropy is sort of a rough guide for how far we are from having the full system decreased to zero. Now, Hawking computed his using a thermal state, and the 1993 Don Page curve really got the quantum gravity community excited, because this made more sense from there, but still people thought, well, we need a full quantum gravity theory to understand how we can do this. So in his 1993 also, Nobel Prize winner Gerard, I don't know how you pronounce it, but 't Hooft discovered the duality between gravity and conformal field theory in one dimension less. Unfortunately, the title of his paper was Dimensional Reduction in Quantum Gravity. And everybody read that and went, who the hell cares? And never read his paper. Now, a couple of years later, in 1995, Lenny Susskind rediscovered it and called it holography. And we had a whole new insight in 1997 when Juan Maldacena created the anti-de Sitter conformal field theory correspondence, sometimes called the Maldacena duality or gauge gravity duality. It's conjectured relationship between two types of physical theories. First, you look at an anti-de Sitter space, which is used in some theories of quantum gravity. And on the other side, you have the correspondence between conformal field theories. These are quantum field theories, very similar to Yang-Mills theories, which are the basis of QCD. Anyway, so this is a picture that you might think about it. The anti-de Sitter space is a space which has negative curvature, not flat the way our universe is. And the quantum field theory is on the, you can think of gravity in a box, an anti-de Sitter space box. So inside the, what's called the bulk, the p+1 dimensions is where gravity works. This is general relativity. On the surface, you have the quantum field theory, which is, as I said, basically Yang-Mills kind of theory. And the duality says that anything you can do in the quantum field theory is equivalent to something going on in the gravity of one higher dimension. Of course, you can do it in the reverse. Since it's a duality, you can do it in either direction. It's an isomorphism in mathematical terms. And when Maldacena said it in 1997, it was simply a conjecture. Now, since then, Witten has shown that approximately 80 to 85% of the duality is accurate. He's not shown that it's completely accurate, but he's shown that the tremendous, great majority of it is accurate, and everybody assumes that if Witten never gets his act together, because nobody else is going to be able to figure it out, but he'll eventually be able to figure out how to make it completely accurate. Anyway, this is what's called ADS-CFT or holography. So in holography, a black hole is just another quantum system. So that means that a black hole in ADS is just a non-gravitational quantum system. So unitarity, of course, has to be true. A non-gravitational isolated quantum system doesn't really result in information loss. So those systems evolve unitarily. So the gravity, the information of a black hole has to be has to be conserved. Now, the problem with this, of course, is that we don't live in anti-de Sitter space. First of all, it has the wrong sign for the cosmological constant. Instead of expanding, it's contracting. And second, it's got a negative curvature rather than flat, which is the de Sitter space that we are in expanding. So a lot of work has been going on trying to create holography in de Sitter space. And although they've gotten a few things sort of to work, mostly it's just been a failure. So that was sort of the next step. So there is a way to save the information paradox, but it's in a space that doesn't make sense and got the wrong curvature and the wrong expansion. So just, it's a little crazy. Starting around 2015, Tom Hartman, Neil Turek, and several other people went back to an old paradigm, the path integral for gravity in standard model of particle physics. So this is this is the standard model of particle physics, and you can do a sum over relevant classical solutions, and you can get a semi-classical limit and a contour integral, all kinds of stuff going on, which we're just not going to talk about here. But using Feynman's path integral formula for quantum field theory, the solution for those kinds of objects are using saddle point methods in asymptotic approximations. Now, in our alternate lectures, we're going to be talking about such asymptotic series using saddle point methods in a couple of weeks. These are far field solutions, and in order to get them, you need a saddle point. Unfortunately, everybody assumed that a saddle point existed in the previous types of computations, but they didn't have one. That is, not until recently. So in 2015, Netta Engelhardt and A.C. Wall found a saddle point in 2021. They also found another one. So there's at least two that can be used to compute the solution of the gravitational path integral. In 2019, Alamari, Engelbart, Morolf, Maxfield, and Pennington, using the 2015 saddle, were able to compute 3 points on the page curve. Not the entire page curve, only 3 points. The one that everybody knew originally, which is the initial 0, the maximum 1, and when it goes completely evaporated. So using the gravitational path integral, they were able to calculate 3 points on the page curve. There are some limitations. The first is that the classical gravity that we're talking about in our space-time is of fewer dimensions than our space-time. This is sometimes called Polish gravity, made by a Polish physicist, Jakub. And the second problem with this is it's even more non-locality than quantum field theory. So if you've ever looked into, what are those boxes? Can't think of it. I'm sorry, I'm just dropping out. Anyway, there are some computations that have been done that have shown degrees of non-locality, and you can have quantum field non-locality, you can have a stronger kind of non-locality, and you can have complete non-locality, which is what Newton did. And so the kind of non-locality that's done in these calculations is spunkhafte Fernwirkung, the spooky real spooky at a distance. So that's been the success, and everybody thinks this is a strong indication that eventually using these kinds of techniques, rather than needing a real quantum gravity, they're going to be able to complete the page curve rather than just 3 points on it right now. So there's not a solution yet, but it's a pretty interesting solution. And the non-locality has to do with the lack of firewalls around event horizons. The people in the group here, Alamari, Marolf, Maxfield, and Polchinski, were the people who created the firewalls. And they had shown that you'd have these firewalls, but if the material was non-local, even stronger than quantum field theory, you'd avoid the use of firewalls. So this particular kind of calculation shows that not only that there are 3 points on the page curve and a hopefully smoking gun that Hawking information paradox is wrong, but also that the firewalls, the fact that we don't see firewalls is because of the non-locality in the calculations. So this, of course, all continues going on as we're talking right now. As far everything that I've looked at has been until 2021. I haven't seen anything new in 2022. I'm sure there is, I just haven't seen it yet. Anyway, okay, let me pause the recording once again. Okay,
Hi,
so
Bob.
questions.
Yeah, I have a quick question. I'm still worried about the entropy of a pure state. I think of a pure state as some vector in a Hilbert space, and I don't see where the ensemble comes from.
Well, you keep increasing the size of the system as the size of the black hole increases, because everything that comes in becomes part of the system.
Yeah, I understand all that. I just don't see that size, where that comes in as far as thinking of what a pure state is, how it is represented as a vector in a Hilbert space. I'm not sure where size comes into that picture.
Well, we're averaging over the Hilbert space. We're doing semi-classical gravity. I mean, quantum field theory, not pure quantum field theory.
Okay, so we're talking about an ensemble of pure states that we're averaging over.
Right,
Okay, well, that,
right.
all right.
Okay, so I apologize. I should have said it that way. But anyway, yeah, other questions?
I am wondering if anything has to do with that. I just recently read about the broken symmetry and Higgs bosons. Has that anything to do with this problems here?
Do
I don't
you-
know much about it because I just read it in a semi scientific book, but it just occurred to me that I remember that Hawkins did not like to accept the Higgs boson's existence up until it was discovered. And that was that hidden symmetry and broken symmetry question. I don't know.
Well, as far as I know, there's nothing to do with hidden symmetries or broken symmetries. This is all about semi-classical quantum field theory. So you're averaging over the Hilbert space. This is,
I'll go in 1 second.
yeah.
Oh, no problem.
So I don't think there's anything to do with it. As far as I know, it's completely independent. Steve, do you know anything?
No, I don't think I can answer that question. I'm not sure I even understand the question.
It just occurred to me that there was a lot of discussion with Hawkins and involving all this gentleman Engelhardt and Page. I had read that, and we disagreed a lot about the possibility of the existence of the Higgs boson, that it cannot exist. And I was wondering if it would be somehow connected to this
Well,
field.
Alamari and Marolf and Polchinski, it didn't have anything to do with the Higgs boson. They were about the firewall.
Well, maybe.
So they have nothing to do with the Higgs boson.
Oh.
Bob, I've got to go, but I want to thank you for bringing us up to date on some of these latest results. It's been very, very interesting.
Okay, yeah, I'm happy to do that. I hope I've kept it at a level that we can call it a Goldilockian lecture.
Really.
It's a Papa Bear Goldilocks
It
lecture.
was pretty good, Bob. It was pretty good.
Yeah,
It-
close
no,
enough.
No, I think for me, it was terrific. It brought a lot of things that I'd been hearing together. It linked them together. So there's opportunity to study at a lower level many of the concepts that you presented.
Yeah, and
Which-
like I said, once I finish the contour integration and then we move on to the saddle point solutions, that's the technique that was used to do the calculations in this. So that'll be the next couple of lectures that we do in the not Goldilocks group.
If you could send on this recording, that would be good.
Yeah, I'm gonna put it in the YouTube channel and then send the link to Bob.
Yes, that'd be great.
And I'll put the lecture in the in my Dropbox and put the link to that so you can download it.
So,
That's
Bob,
good. Thank you.
Okay.
let's talk, maybe you could stop the recording and talk about next week. Are you going to do next week also a regular session?
No, I haven't got enough time to. I'm gonna need 2 weeks, so you're gonna have to do another Goldilocks